Hello everyone, welcome to chapter 7. This chapter we're going to be talking about normal probability distributions, and this is the first chapter where we actually really start getting into concepts that are going to carry us through the rest of the semester. Not that the other concepts we learned didn't carry us, but this is where we actually start really focusing on more statistical methods as opposed to just finding out the mean and standard deviation. We're going to really start applying those in more of a statistical aspect and form. So in chapter 7, we're going to be talking about normal distributions, determining normal probabilities, finding values that correspond to normal probabilities, and assessing departures from normality. So first, let's talk about normal distributions. So as you remember, when we're talking about normal distributions, it's a normal random variable that are the most common type of continuous random variables. It was first described by Abraham de Moivre in 1733, and it was later elaborated by another mathematician called Pierre-Simon Laplace, who elaborated the mathematics in 1812. It describes some, not all, natural phenomena, but the majority of them that we encounter. More importantly, it describes the behavior of means. So let's talk about the normal probability dense function. So if you recall from continuous random variables, remember continuous meaning it's ongoing forever. So we can literally say something just to always think about. We're talking about negative infinity to infinity. And remember, when we're talking about continuous random variables, we're talking about the probability dense functions, or PDFs. Remember from chapter 5. Normal PDFs are recognized by their familiar bell-shaped curve. We're going to show the next slide, which is an age distribution of pediatric population, and the overlying curve represents its normal PDF model. So here we have this histogram with ages and years at the bottom, and we have our normal bell-shaped curve, which I probably won't be able to trace, but you could see all the way. You can see how the bell-shaped curve is done. And so when we're talking about normal distributions, we're talking about a bell-shaped curve here, how it's overlying over a certain amount of data. So, and specifically when we're talking about a bell-shaped curve, we have this curve that of some sort of data set or some sort of interest that we're looking at that has a normal distribution. And when we're really talking about this, we really want to understand the area under the curve. And what do we mean by this? It's the amount of area underneath the curve. So remember, when we're talking about our other types of probability, and we can relate them to bar charts or pie charts and their proportions, right? We're measuring how much is underneath. And specifically for normal bell-shaped curves or normal distributions, we want to know the area under maybe certain sections or at certain points. So this is going to be shown by darker bars on the histogram in the next slide, and then it will correspond even further on the slide after that, and we'll be talking about that. So here we have our same bell-shaped curve with our years and age, and say we wanted to find the proportion less than 9, so ages 9 and less. So you can see the darker shaded from the value of 9, less is darker, and we want to find out how much area does this actually cover. As you notice, not all the squares here, or the histogram, are the same size. It might be the same width, but they're not the same size. But how can we find the area under the curve? And then what this actually looks like in a more realistic setting is this area. So it's the proportions less than 9 of the area under the curve. And it was originally, we can find it by finding the function of the normal distribution, and that's from this equation shown right up top here. If you wanted to find out the function or the area under the curve, we could place in values of x, find the value of mu, and if we know our standard deviation or sigma, we can find the function of x at that particular area. But remember, most of the time we're trying to find, if we wanted to find the function of x at 9, right, for 9, we have to find the function of x at 9, and then we also have to compare it to another value, right, because we were trying to find the total area underneath this, so we'd have to find it all the way. Remember, this line here and this line here extends infinitely. I think that's one thing to always take into consideration. is it extends infinitely, and we know the sum of it is going to total 1, but it does extend infinitely, so always keep that in mind, especially when you're looking at the charts in the back of the book. Remember that we're only given the majority of information, but theoretically it extends on infinitely, positive and negative infinity. So remember, we would find basically the function of, it would be like a calculus type statement. We would find the function of negative infinity to the value of 9 using this equation up here. Thankfully for us, we don't actually have to go and actually type in this type of function. There is a simpler way to find this out, and we'll be talking about that. So when we're talking about a normal distribution, we're talking about parameters of mu and sigma. Normal PDFs are a family of distributions which are defined by the parameters of mu and sigma. There's also some other characteristics that should be mentioned about a normal distribution, and that is that the mean, median, and mode are all equal, and that the curve on either side of mu, so remember if we were to go back here, we would say mu is going to be defined as the average value, right, the balancing point, and we're just going to assume this would be mu, and that the distribution on mu is going to have a mirror image on the other side. So let's kind of go to a more blank space here so you can maybe see this a little easier. So if we had a line and we had our bell-shaped curve, I'm not very good at drawing, as you probably know, so I will do my best. But if we had parameters normal bell-shaped curve and we had mu, we would say these are mirror images of each other. And if you have mu is going to be the balancing point. So we would say that 50% of the data would be here and 50% of the data would be on this side as well. They are mirror images of each other. And then we know that the total area under the curve is going to equal 1. Other things that we should know about the parameters that we've already kind of talked about is the 68, 95, 99.7 rule and Chebyshev's rule. The Chebyshev's rule, remember, is only when it is not symmetrical, and we're really going to only be focusing on the 68, 95, and 99.7 rule. Mu controls the location of the center. We'll show in the next figure, and then the standard deviation controls the spread. So what this is also normally stated is that in other words, the normal distribution is specified for each different value of mu and the standard deviation, where mu, shifts the graph of the distribution along the x-axis. So if this was mu, but we had a different value, this could shift either left or right, and the standard deviation determines the degrees of flatness or peakness of the graph, right? So this is where we could have a very leptochuric or platychuric type of graph shown here. That is, standard deviation controls the spread, and mu controls the location of where it is done on the x-axis. Often called mu is often referred to as the location parameter, and standard deviation is often referred to the shape parameter. And this is also shown here, so as you can see, mu can shift over here and change the location of the means along the x-axis, and the standard deviation will change the shape parameter, where it can either be either wider or very more close together, and that is how the parameters of mu and standard deviation work together. One thing to keep in mind, and I want to make this a very good point, is that anytime mu or sigma changes, it's a different normal distribution, right? There can be infinite number of normal distributions, right? Because mu can change. Mu can be 2, and then another data set mu could be 4, and standard deviation can be 15, or it could be 2.5. Every one of these is going to be a different normal distribution, and it's going to change. So normal distributions, there are infinitely different numbers, right? Because all mu and standard deviation are doing is changing either the location or the spread of the graph we're looking at. The information is still normally distributed, but there's many different types of graphs. However, when we're looking specifically at this, a very specific type of normal distribution is called the standard normal distribution. We're going to go into that a little in a little bit here, but I want to make that clear that there's only one standard normal distribution, and that one standard normal distribution is a subset of the normal distribution. But the standard normal distribution always has a mean of 0 and a standard deviation of 1. And that is where we're going to be referring to the back of the book in our table. Everything is based off of the standard normal distribution, but just note that of just normal distributions, there are many normal, but only one standard distribution, and we base a lot of information off of the standard into the normal. This is where we can see that this will apply for many things that we see in nature, but not all of them. So the standard deviation has points of inflections where the slopes of the curve begin to level, occur one standard deviation below and above the mu. Practice sketching normal curves to feel the inflection points. You can practice labeling the horizontal axis of the curves with standard deviation markers. So what you can do is, if you have a normal bell-shaped curve, once again, mine are not very good. I am not an artist. I don't claim to be one. But you would take your fingers and you can run them along this part here and take it and run it along here. And you should feel at the point where the inflection, this is what they're talking about, the inflection points. And this is where you would normally classify where one standard deviation above and below the mean would be. I'm not very good with that. I can visually see it maybe a little better than feeling it. But once again, a lot of books talk about the feel of it. I've tried it. I'm not very good with it. But one thing that's very good that they talk about is practice sketching. We'll be going through some videos and practice sketching where we are looking for certain areas. So if we're only looking for certain areas on a graph like here, or maybe we're only looking for a particular area here. Normally, if you practice sketching what you're looking for, you can see it and visualize it better. I will do my best to draw them out for you so you can see it, but the biggest thing here is to practice sketching it. So a lot of times you might, once you sketch and see what you need to do, it might help you set the problem up and solve for whatever you're looking for. Once again, here's these points of inflection with an actual better bell-shaped curve. And if you were to run your fingers up the side, you should feel the inflection points about here and here, which this would signify -1 standard deviation and +1 standard deviation from the mean. So mean and standard deviations, once again, the mean and standard deviations from the data are denoted as x bar and x, notated as x bar and s. And the mean and standard deviations for parameters of the normal distribution are mu and standard deviation. The means and standard deviation are related but are not the same thing. Remember that for x bar and mu, we're calculating it the same way. However, for standard deviations, depending on if we're looking at it from a population standpoint or a sample standpoint, the equation will change slightly for the degrees of freedom. However, for this class and our purposes, I'm not throwing any tricks at you. We will always be calculating standard deviation as if it was a sample. And then this is where we get into inferential statistics, and we can take a sample and infer it to the population. So for us right now, we're just going to be worrying about the sample, not the other way around, but note that there is a difference. And then we're going to get into now, so we've learned about the normal distribution, standard normal, bell-shaped curve, how mu and the standard deviation play a role in this, and that we're really going to get into now the 68, 95, and 99.7 rule, which, as you can see from the graph below, that 68% of the area under the curve will fall within ±1 standard deviation of mu, 95% will fall in ±2 standard deviations of mu, and 99.7 of the area curve will fall under 3 standard deviations of mu. So the next couple slides are going to be going over this entire concept. And actually, we're actually running out of time now, so we're going to pick this up on the next part, but really start looking at these graphs because they're all saying the same thing, where if you're ±1 standard deviation from the mean, it's going to encompass 68% of data. Now remember, this is symmetrical, and it's even on both sides of the graph here. All right, take a moment, look at this, and we'll pick back up talking about the 68, 95, 97 rule in the next video. See you next there.